Hello, here we're going to look at 6.1, graphing exponential functions. I want to start off with an example of an exponential function. We won't get to see a corresponding video with it, but what happened in the video is that there was a hot cup of coffee poured, and the coffee at time 0 started at 200 degrees. Because this is going to be degrees, and x is going to represent minutes. So, when a thermometer was first inserted into the cup of coffee, it was 200 degrees. And then the video does a time lapse, stopping every 5 minutes to where we could track and see the temperature of the coffee. And so, with that data, we could fill out the chart. After 5 minutes of cooling, the coffee was down to 170 degrees. And then at each 5 minutes after that, it continued to cool. Now what we're going to do is we're going to make a graph of this data, look at it, and see a new type of function that we'll be able to work with, called exponential functions. So I'm going to start us here at 0, and I'm going to count over every 4 and make that our next spot. That'll cover our 0 to 25. And then for the temperature, I'm going to do a break so that I can start the graph a little higher than starting it at 0. I'm going to start it here at 120. And then every 4, I'm going to add on 20 more degrees. Alright, and once we have that set up, what we'll be able to do is plot these points. So at time 0, it was at 200. At time 5, it was at 170. At time 10, it was at 155. At 15, it was at 142. At 20, it was 135. So here would be 130 halfway in between. So here's 135. And then at 25, it was at 127. Now what you'll notice is this is not linear. This has a curve to it. And the curve looks like that. And the temperature would continue to drop. Now, one thing that's important to note is that this room temperature that this experiment was happening was at 68 degrees, was the room temperature. Now, what this type of curve is called is exponential decay. We're also going to study exponential growth, but food cools at something called exponential decay, to where it loses a bunch of its heat right away. Because in the first 5 minutes, we dropped 30. So it lost a lot of heat right away. But then after that, it started to lose smaller amounts. This next part here, it lost 15. This next part here, it only lost 13. The next part here, it only lost 7. And then the last portion here, it lost 8. Now, this was just recording measures off a thermometer in the coffee cup. It's not going to start losing heat faster again. So these two guys here, especially this one, is a little bit of a recording error in terms of how much temperature it lost. And we can see from the curve, it is actually going to continue to curve down, but it starts to get very slow in terms of how quick it's decreasing. You can see from the graph that, right here it lost a good amount. Here it lost a little bit less. Here it lost a little bit less. Here it lost a little bit less. It'll continue to do that. And this curve actually, if we were to zoom out and make our graph larger, would drop all the way down to room temperature at 68 degrees. Now, it would take it a very long time to do this. And I don't know if you've ever interacted with coffee or another liquid that's cooling. It does stay a little bit warmer than room temperature for a very long time, but it also loses a lot of its heat right away. Now, you may have experienced this with pizza bites out of the oven. When you first get them out of the oven, they're probably closer to 350 degrees or whatever they bake at. They're very, very hot and they'll burn the roof of your mouth. But if you let them cool for too long, say 10 minutes, now they might be too cold. And that's what exponential decay is. It loses a lot at first, and then its growth in terms of how much it's losing starts to get smaller and smaller. So maybe you found it challenging before to find a good time to eat your pizza bites, because when they're out of the oven, at first they're too hot. If you wait a few minutes, they might not be hot enough, and that's because there's really only a little bit of a window here to maybe where it's going to be in a comfortable temperature. And for this coffee, say you like to drink coffee between 140 and 170 degrees, you only have a 10-minute window where that's going to be the case. Up here it's too hot, down here it's too cold. That's exponential decay. We're going to come back to exponential decay, but we're going to go ahead and switch over to exponential growth. An exponential growth function has the form y equals bx, where b is greater than 1. Now, another thing that you'll also see this commonly listed with the letter A. That A is a translation, just like we've been working with. We'll notice our same old friends. A, which is going to change how fast we grow with a stretch or decay. So this is a stretch or compression. We have our old friend H value up here, and it moves us left or right. But it does in fact do the opposite of what you'd expect because of that negative sign. And then we've also got the K value, which that moves us vertically up/down. All right. So here's some information about exponential growth. The first part is the most important, to where b must be greater than 1. Because what exponential growth is going to be is some number here. We watched a video yesterday about that piece of Bible paper that was doubling each time. What that would look like is this, 2 to the x, to where that piece of Bible paper was doubling each time. The b value is what you're multiplying by over and over again. The reason that it must be larger than 1 is because if we plan on having growth, the number that we have to multiply by can't be 1, because if I multiply by 1 over and over again, I stay the same. But instead, it must be larger than 1, because if you're multiplying by a number that's larger than 1, you will grow. And then there's some other pieces of information here. One we covered back in chapter 2. It's not saying anything that will directly impact us today. The domain for these is going to be all real numbers. And then there's going to be something called an asymptote, which we're going to look at here in a moment. Range will be impacted, will be different as we change some of our k values on these. But for the most basic graph of y equals b to the x, it's what's called all the non-zero numbers, and the graph contains the point 0, 1. So let's make a quick sketch of what a graph here would look like for y is equal to b to the x. It's telling us we're going to have a point right here of 0, 1, and then it would grow like this. And what it was talking about for that asymptote is something like this. Now, I'm not able to get straight edge tools on here, but this curve will never actually touch the x-axis, nor will it ever cross the x-axis. And we'll see how that's going to happen mathematically, but that's called an asymptote. A real-world example of an asymptote is on this coffee problem. If we left this coffee sitting in the room for 2 weeks, it won't continue to get colder and colder and eventually, get to 32 degrees and turn into an icicle. It would instead approach the asymptote of 68 degrees. So if we extended this graph of the coffee to, I don't know, days even, so lots and lots of minutes, so let's just say 24 hours, 48 hours, what we would find is that the graph, kind of would curve in and stay flat at 68 degrees. But it would never go below 68 degrees because that's just not how things work. If you leave the coffee in the 68-degree room, it'll eventually get to 68 degrees and stop, no matter how long you leave it sitting there. That's an example of an asymptote. It's to where it can never cross it because it just wouldn't make any sense. Now, the reason that the most basic type of function will always cross through 0, 1 is because if we plug in the x-coordinate of 0, we know that from our rules of exponents, anything to the 0 power is 1. So that's why whenever we have 0 as the x-coordinate, the y-coordinate will be 1. Now that will change as we start to mess around with a values and k values. But for the most basic type, it crosses through 0, 1. So let's start to do some examples and see some scenarios of where we have h and k values and how that will impact things. On this first example, I went ahead and filled in the table for you. If you're curious about how to fill in tables for exponential functions, it's just like any other scenario. So here's our equation, y equals 4 to the x plus 2. You would simply go through and evaluate by replacing x with the value that they wanted. Now in this case here, remember that anything to the negative power actually requires you to take the reciprocal. So 4 to the negative 1 power is actually 1/4, 1 over 4. And that's where they got the 2.25, because 1/4 is 0.25 plus 2 is 2.25. And then for all the other ones, we are simply replacing x, this x right here, with whatever they tell us to. So we'll have 4 to the 0 this time, plus 2. Anything to the 0 power is a 1. That's where they got the 3 from. And you could continue this on out. 4 to the first is 4, plus 2 is 6. And if you continue to evaluate, that's where these different y values would come from. And when you graph it, you'd get a curve that looks like this. And it asks us to talk about the domain and range. The domain is always going to be all real numbers for exponential growth and decay, because this guy here is going to the left forever, this guy's heading to the right forever, so that's all real numbers. Range, though, is going to be different. Range is going to be impacted by the asymptote. You can see here in this graph that this curve is starting to go flat right along here on 2. It would actually continue to do that. And the reason for that is if I start to plug in other values of x, like if I plug in -2, 4 to the -2 power is 1 over 16. And sorry, this should have been a 2. So on this one, we'd get 2 and 1/16. If I plugged in x as -3, I would get 4 to the -3 power plus 2. That's 1 over 64 plus 2. So I'd get 2 and 1/64. And you can see that this fraction would start to get closer and closer to basically not even mattering. The next one would be 2 and 1 over 256, which is super, super close to 2. That's why this has an asymptote at this dotted line here of 2. And the way that that'll impact our range is that our y values will always be greater than or equal to 2. So we'll have to look at the asymptotes, and we'll soon learn that the asymptotes are the asymptote, because there's not going to be multiple, the asymptote singular will come into play with the k value, because it naturally starts at 0, and k values move it up and down. So there's a brief introduction. These are, have a lot to them, so it's going to take us a while to talk about the different scenarios that can occur. Let's graph some examples. We're going to graph each function and then state the domain and range. So on these, you can simply make a table. So I'll toss in some negative values and some positive values. And then you find them by evaluating. So right here, 3 is going to wait, because I must first do 2 to the negative 2 power, which is really telling me to do 2 squared, but to put it in the denominator. 2 to the negative 2 power is 1/4. And then when I multiply straight across, we'll get 3/4, which is, 0.75. When I go through and evaluate at -1, we'll get 3 times 1/2, which is 3/2, which is 1.5. And then at 0, 2 to the 0 power is 1. We'll get a 3. Here, we'll get a 3 times 2 to get a 6. And then here, we'll get a 3 times 4 to get a 12. Now, before I even go to graph it, I want us to notice what happened here. The initial equation told us that we were multiplying by 2 over and over again. And you will hopefully see that here. Here we multiplied 2. 3 times 2 is 6. 6 times 2 is 12. 1.5 times 2 is 3. 0.75 times 2 is 1.5. So you can see how this is exponential because I'm multiplying by 2 each time. What this 3 tells us is where we're starting. It tells us that 0, 3 will be the first point. And now we could graph it. Now, a lot of times on these, you'll need to scale them to get all the points to fit. So what I'm going to do is I'm going to count each line as 3. And then I'll graph it from that perspective. So we had 0, 3. We had 1, 6. 2, 12. -1 was at 1.5. -2 is at 0.75. And you can see that curve taking shape. It would start to grow very quick because the next entry on my table would have been 3, 24. If you wanted to add on another spot, it would be all the way up at the top here. And no matter how far we went into the negatives here, this would never quite reach 0. It's going to have an asymptote there. And remember that these naturally have an asymptote at 0. So if there's no k value, so in this case a +0, that's what we'll use to help determine our domain and range. Domain is always all real numbers. The range in this case is going to be y is greater than 0. We will never reach 0. 0 there, but I can be anything larger. Let's graph some more of these because it's going to take us some practice here to get this accomplished and to understand how these work. Now, we'll ultimately be able to type these in on the calculator as well, but I did want you to have an understanding of what makes these exponential functions work. For this one, let's draw up a table. If you've been following so far, hopefully you'd recognize that I'm going to start at 0, something, and that something is going to be this number here. Like on this example, it was a 3, so we had 0, 3. Now, in terms of making other values for this, we have a couple of options. I could go through and I could evaluate this function, 1/3 times 3 to the x. I could substitute in all the different x values and find out the number. The other thing that hopefully you might understand now, though, is that this 3 is telling us that we're multiplying by 3 over and over again, which means I could just do that to complete the table. 1/3 times 3 is 1. 3 times 1 is 3. And if you don't believe that's true, look what happens if you were to go through and plug in 2 as x. You'd get 1/3 times 9, which equals back to that same 3. Now, you might be wondering, well, how do I go backwards, Mr. Cottle? Well, there's a couple options. You could think what number times 3 gives me 1/3, or if you want to go backwards, we're essentially dividing by 3. So this one would be 1/9, and this one would be 1/27. And now we have enough to graph. And I'm not going to have to scale on this one because it's going to be plenty tall already, because the 1/3 slowed us down. Yes, we were tripling each time, but with us starting off at 1/3, we didn't have enough time to get really large. So at 0, we are at 1/3. 1 was 1, 2 was 3. And then we had our asymptote taking shape here, to where 1/9 is barely off the ground at all, 1/27 is barely off the ground at all. There is our asymptote. So remember, it's going to come across the x-axis there. And off this one goes. Its domain for all of these will be all real number. Its range, however, will be impacted by k values. This is another example where we didn't have a k value. So its y is greater than 0. For the next two, I'm going to have us type them in on our calculators and use the table to get them graphed. So I'll give you an opportunity to do that. Now remember, to get this typed in on your calculator, you're going to want to push, after you go to y equals, and you go to that part of your calculator, you'll type in the 4. You'll need to use the up button to get up into the exponent, and you'll want x minus 1. If you want to be extra careful, you can put parentheses around your x minus 1 to help your calculator understand that the x and the minus 1, the x subtract 1, are both in the exponent area. And when you type that in and make your graph by using the table function in your calculator, your value should match with what mine are going to be here. Now, I may have included more values than you did, but I was just pulling these off the calculator, and I wanted to show you that this exponential growth does indeed get very large very quickly. Another thing I wanted to mention was the starting point. The bad news on exponential functions is that the starting point, like this 1/3 or this 0,3, are really only able to be easily found when we don't have any h or k values. H or k values make those harder to track. So, using your graphing calculator and using a table is really the most reliable way to get these graphed, or simply, taking your equation and writing out by hand, by filling in for x, what you wanted and making your own table. When I go to graph this one, and I'm not going to worry about scaling, but we had 0.25, we had 1, 1, we have 2, 4, and then off it would go. And you can see these numbers here getting smaller and smaller, but since I don't have a k value, my asymptote will start right here on 0 and curve up. So our domain is all real numbers. Our range will be, once again, y is greater than 0. And that's what's going to be most of the time until we see a k value. This one's going to have a different range, so we're going to discuss it. Now, when it comes time for graphing this, we could make a table. You could plug it in by hand and do the exponent and then subtract it by 2. You can also type it in on your calculator and graph it that way as well. And regardless of which path you choose, once you go to make your table, you'll see that you get these values. All right, so you'll notice that this one goes into the negatives. And all of our previous ones had not done that. They'd all stopped at 0. The reason we're going down into the negatives is because of this k value subtracting 2. If you go to plot these, it'll look like this. Negative 2, 1.89 is almost down to negative 2. You know, this one's starting to climb back up here a little bit. We have 0, 1. We have 1, 1, and then 2, 7's already off the page. Our new asymptote, because of that k value, is going to come down here and be negative 2. So we have an asymptote here now, based on that k value, at negative 2. That won't impact the domain. These guys still go left as far as they want and still go right as far as they want, but it will impact the range, which will now be y is greater than negative 2. We will never reach the value of negative 2, which is that k value. So in future videos, we'll look at decay. They'll operate similar, but they have their own specifications to them. And graphing these takes a little bit of work. There's a lot of understanding to be had that we just covered. If you're able to type these in on a calculator and go to the table and get them graphed, that's ultimately the most important skill that you will need. You won't necessarily need to be graphing these by hand very often. So typing them in on the calculator to generate the tables can be a very valuable skill to have. Now, we spent a lot more time talking about some of the inner working pieces so that you could understand it. But ultimately, if you can graph these on your calculator and then be able to make a graph, you'll be in good shape.